My friends, the last chord in this beautiful symphony of the Yuval Fest will be struck by Yuval Neeman. Yuval, a leading world-class scientist, a scientific leader, and a statesman of science. It is a privilege and great pleasure to call on Yuval to present the closing lecture of the conference.
Before I start and consider this as still a comment on the previous lecture, I wanted to say that when Wagner was here, I gave him I have a collection of scientists on bills, and I gave him 2 bills. I don't know if he's used it or not. 2 bills of one is 5 dinars and one is 5 million dinars with Tesla's picture on them. That is, and the hope was that the accelerator would really not make that kind of jump in cost. But this is they are Yugoslav bills or Serbian bills. Let me start, if I find the right direction in which I put the things here. Yes. Let me start by saying one word, and this is, I wrote it up here so I shouldn't forget it. It's over there. Also, I'll have to go there with all of this. Okay. Yes. So, thanks is the word I would like to. No, I think the word, yes, upstairs there. Thanks. So, thank you very much. Thank you, Aaron, and the people who organized the whole thing here. Thank you, my friends from all over the world, and who contributed in such a fantastic way. And I must say that I'm really, I don't know what to say, because it's shocked in the positive way somehow. So it's an anti-shock. I don't know how to call it, but white shock. So it was really a fantastic experience, and maybe a real compensation, some compensation for all the problems I've had in my life, because yesterday lots of things were mentioned in which I had a hand and which succeeded. I also have quite a list of things I tried to do and which never got anywhere or were demolished. And so yes, thank you. I'll use this at some stage. So that is the first thing. Thank you very much. And also the gifts that I got, I'll write thank you letters to people personally. I'll try to. That's one of the promises that I've sometimes not kept, and my conscience has been nagging me at that. So thank you very much, including that book, the Josephus. I of course have Josephus, but this edition with the illustrations of the 19th century and so forth was such that even Dora, my wife, agreed and took it enthusiastically, because you should know that with the number of books I have, the pressure was to not to. She has been shocked every time I got more books into our home. Recently, I gave all the science fiction as a gift to a library, so as to make room for other things there. So thank you very much, all of you. And now the talk I'm going to try and give now in that state is a a candidate for another candidate for a Mach principle kind of thing. There is a song Matchmaker, Matchmaker in Fiddler on the Roof, and I would sing it as Massmaker, Massmaker. In fact, the Higgs field as such is, some people here have been involved in the Higgs field, is a mass maker, and I'm going to discuss this from the point of view of perhaps a candidate for the production of inertia. Now, I'll explain, those of you who know the history of general relativity know that there was a long discussion started by Einstein because of a book by Mach, which was a textbook in mechanics, and because of that, the question was whether this, whether inertia was once you decide that there's no absolute space, how do you explain inertia? And there is, among friends I've had, there was the late Dennis Shamma, who wrote a little book on that topic. And I remember having enjoyed the book even a long time ago, before I was a physicist. And I think he wrote the book in the late 40s or so, I think 47 or something like that. And now, to my surprise, I find that a model that I built up recently for other purposes, and which I hope will be confirmed by the result of about where to find the Higgs that Professor Zergel has talked about, also gives this kind of possibility of doing something, of being perhaps responsible for the creation of inertia of mass. The conclusions that in the period of the discussion, the conclusions that they came to was that you can explain inertia only if there is a connection between the body and the distant masses of the universe. Why the distant? Well, first of all, because even Newton measured the force close by, and it's not going to do anything. And you want inertia to work in a uniform way and so forth. So it's got to be, there are lots of reasons why it has to be done by an interaction between the body, any body here which we try to push, and the distant masses of the universe. Because of that, it's got to be a force that, well, the force is 1 over r and not 1 over r squared. Because 1 over r squared, and you take a sphere, or not a sphere, an envelope to a sphere. It's 4 pi r squared multiplied by the thickness. So the r squared cancels. You don't have a force which is then mostly in the hands of the distant masses. But with 1 over r and some other reasons, it works. So that was the idea, and I gather that there were calculations that were made, various calculations. I'm not, I don't know the details about some of these calculations. In the book by Wheeler and 2 collaborators, there are a few pages about these calculations. What I'm going to show you is, I think that it could be done in a different way. So whether that has anything to do with inertia or not, you be the judge. The model I'm talking about is, maybe I should say that in thanking, like I thanked everybody here, I should thank 3x3 matrices for my the most successful parts of my career. It's difficult to imagine how much one can get out of 3x3 matrices. And after SU3 and and U3 with the baryon number 1/3. After that, I had also an encounter with SL3R and the infinite dimensional representations of SL3, especially the double covering, which was considered to not to exist in most textbooks, and which I managed to build. But that one, the one with SL3R, still has not passed away the point of success, in the sense that people would use it and that it would become an everyday thing. I think partly because of some advertisement mistakes that we made, George and I, at some stage, and we'll have to, perhaps in next generation it will be appreciated. But the latest one was SU21. SU21 is a supersymmetry. It's a super algebra, and when the homologue of the Gelman in that case is named David Fairley, and he came to the same group, to the same idea from a different direction. We published in Physics Letters. His came about a month after mine. I mean, same journal, etc. He came to it only from the dimensional reduction, and I came from a different direction, and that direction is connected with what we just heard in one of the recent last lectures, and that was the idea of a connection. In fact, what Friedrich showed us about what is a connection, it's become so that there is now a theory of the superconnection, and this is part of that model. A connection is really what we call a potential in terms of physics, in that sense. And my model incorporates what the weak interaction, the electroweak is doing, but in the form of a supermatrix, not a matrix, but a supermatrix. The commutation relations are very simple. I mean, we have the SU2 subgroup, and the even part of the algebra is going to be, I denote with A, B, and C. That's an SU2 and a U1. And well, maybe I'll show the matrix, and then I go on. I won't deal much with matrices, but just I owe them that kind of thanks. Show them around these matrices. Well, here is my superconnection. The superconnection has in this part there's the SU2, so you have the W plus and the W minus, they're isospins, and in this part you have the electromagnetic field and the Z naught, all of that line, and these are the odd parts of the matrices. This is the Higgs field, and that is the conjugate of the Higgs field. Now, this is being a superalgebra. Between this and this part and itself, it's a commutator. You use commutators. Between this part and itself, you use anti-commutators, and between this and that, you use commutators. So, what you have here is just the standard model. I mean, the electroweak part of the standard model, except that the group defines what is the angle, the Weinberg angle, and it is forced to be sine squared theta equals 1/4, which means that the experimental value is 0.225 or something like that. And this has to be 0.25, so it means that the point of energy is a bit removed, and you can calculate the corrections, and it predicts that the mass of the Higgs has to be two W masses before the correction. That's 170 GeV, but if you put in the correction, it reduces it to around 130, 35, something like that. So that's with respect to this algebra. Now, why do I say that this has anything to do, I suddenly realized that this can do things with respect to Mach's problem or Mach's principle, and this is the following reason: when you the Higgs field is we use it to among other things, it gives you a Yukawa term to the fermions. Now, first of all, let's see here the representations of this algebra it acts on the three state neutrino left, neutrino left, electron left. That makes an isospin, a half weak isospin, and then you have the electron right. If there is a neutrino right, and there is one because we heard that there is small mass, so it exists, then it will be a singlet here. Now, if you take the fractional charges, you get that algebra exists also in 4x4 form. So it seems not to be an accident. I mean, it's something fundamental. The reason is that SU2-1 in the classification is also has the same structure than the autosymplectic in 2 and 2. And that gives you a four-dimensional representation which fits perfectly for the quarks. So the fields are here. You act on them with, in general, you act with the covariant derivative on the fields. Now, what is the role of the Higgs field as connections now? The role is the following. So I'll take here the point of view of, for instance, non-commutative geometry. It's a matter of construction. What you do is the following. You think of a gauge theory in which the base space is made of two pieces. There is a piece of the base space which carries fibers which are left chiral, and there's another piece which is right chiral. You separate out the two pieces. You have four-dimensional space in which they are only left-handed, and four-dimensional space which is right-handed. These two pieces have fibers on them, so here we have, therefore, the nu left and the E left, and here we have the E right. These are the fibers. Now, if you want to gauge, and you want to write a covariant derivative for parallel transport, when you do it for this part, you use the ordinary covariant derivative of weak interactions, weak electromagnetic interactions. Also, if you do it here. But suppose you want to parallel transport from a point here in that fiber to a point X in this part of where the base space is left-handed, left Lorentz, to a point Y in the other part of the base space, on top of another part of the base space. So you need the following things. You need a derivative that will take you in a discrete form, will jump from the left to the right. This is called a matrix derivative, and it will be just a 1 here and a 1 here. It's not really a 1, it's an I here and an I there is square root of -1 because of the various ways in Hermitian. It has to be anti-Hermitian, etc. So you have it here. That makes a jump. So you would first of all jump to the other side, and then you also have to change from X to Y. And it's the field that sits here, it's the Higgs field that works now extra hours as a connection. In the ordinary theory, it is an interfering field. It is a field that breaks the symmetry, but doesn't have a proper honorable job of its own. In this case here, it is a part of the connection, and it does this job. It goes together with the matrix derivative, which is the constant here and here, and it fixes up the question of parallel transport. So this theory has, for its derivatives, in fact, the whole Lagrangian of the weak interactions is one curvature squared, because the curvature contains, you see, the square, this term will give us, with the phi, will give us the phi squared term of the Higgs potential. The anti-commutator of these two places squared will give us the phi to the fourth term. So everything comes out in one shot in this theory. Now, I was not going to go into details, too much details about this theory, but now why do I think that it can do something having to do with Mach's principle? Because the Higgs field now, with this new honor that it has to be a connection, and it's really a gauge theory, so anywhere where there is matter is carries the SU21 charge, because matter is either leptons or quarks. So leptons and quarks will always be carrying these charges. Because they are carrying these charges, they will also induce a field around them. So it means that the Higgs field now has to exist anywhere where there is matter. It will emanate just like the electromagnetic field is induced by an electric charge, and the Young fields by any kind of theory that is there. So the presence of matter in the distance will be the presence of matter with its Higgs field. Now, if you take a scalar potential and you ask what is the behavior of a scalar potential in terms of the force, it will be a 1 over r force. So it has what it takes to help in solving Mach's principle, whether it is doing it uniquely or whether it shares with gravity something, or how that will have to be left to further negotiations. But in terms of candidacy, I think that one of the conclusions of putting the Higgs field into this structure is to turn it into a natural radiation radiating from matter anywhere, and then it has all the properties that are necessary for their job. Now, I say it's an idea which is still very fresh, and what I have here is the sketches that I made about them. But I think that one should consider these possibilities and look back at where were the problems with the Einstein-Mach discussion and the calculations that came after that, Shammas and the other calculations, and see whether that is an alternative, a companion, or I don't know what precisely the status will be. But this is why I called it matchmaker, because this is really the potentiality of the Higgs field in that case. I will be happy to hear comments from people about this idea, which is entirely fresh and new. At this point, I think I will not, well, the way to know whether this is true or not in terms of the particle would have been if the Higgs field is found at the correct place, the correct prediction. There is now an issue of physics reports which is entirely dedicated to these calculations. But the trouble is that after we published at the time the first prediction about that, I think some other theories also came to the same place I mean, predict also that it's going to be around 130 or 100, and I don't know what the other predictions are. Professor Zergel, do you know, what do you expect to have the, I mean, what are the possibilities? If there are too many theories that point to that same place, it won't be considered as a victory of this theory. So I hope that they will predict something else, and that will have the field to this theory by itself. At this point, let me go over now perhaps to a few more general things, but let me say that there is a philosophy that many people apply, and which is a philosophy of laissez-faire. I was generally very unable to laissez-faire and let it happen, and that's it. And I intervened. I fought. I tried to change things, and it's good when things are somewhat in the academic atmosphere. It's not too bad. And for instance, I can take astronomy in Israel. I succeeded in having the observatory for optical astronomy. I failed twice with, I wanted to have radio astronomy. And once because I had prepared people for the job, and when they came back after studying elsewhere, the industry offered them tremendous salaries, and they went away, and that was it. And the other time was the money went away. Or solar astronomy I wanted also. That partly succeeded also, partly failed. I can have a very long list. So I generally tried. I can say now that it's good, at least if you do, then persist on it, persist on these things, because there'll be enough things that, because of entropy, will not work out. And so you need to, to be satisfied that something will come out of what you've been doing, you need to have enough volume to show up after all that entropy. I have, one of the great pleasures is to know that I've had something to do with bringing to Israel, helping our colleagues and brothers in Soviet Union to get to Israel. And that was a tremendous job in terms of the effort that it required and the persistence. And sometime I know that I've been called in Pravda and in Izvestia the enemy of the Soviet Union and all kinds of other things. Sharansky told me that in his trial I was mentioned as one of the people for whom he was spying and so forth. But so I'm not sure that in terms of my career, what I've done, that whether the mix of things that have to do with academic life, things that don't have to do, will remain. But you can't change your nature, and you do what you can with this thing. I know that from the point of view of what I left as a mark, you can find in the literature an Israeli correspondent saying that I must be crazy, and you see it according to my eyes. I mean, etc. So you should be ready for a very mixed kind of result, and then either it depends on your mood whether you look at the half empty glass or the half full part of the glass. And you have helped in making me look at the half full part during these days. And so I hope that the effect will last. And maybe I'll be in a better mood to do further things in the coming years. If I have years, the rest, I don't know. It's according to what Chaim said yesterday, it's a matter of changing base from 8 to 10. Change of base is a complicated thing in mathematics. So thank you very much, everybody.